Hello everybody, I hope you all are doing great. Let's start today's lecture with a question. What piece of equipment would you choose or would you use if you want to have a lot of flexibility to move in different directions and cover an almost large area, radius of area, and or if you want to excavate a surface which is lower, which is under the natural ground level. The answer to that, as the title of the lecture is showing, is hose. You would use a hoe for all those situations. But what are a hose and how can we use them, or what are they good for, and how can their production be computed are the questions that will be answered in this lecture. So let's get started. All right, so a hoe is primarily used to excavate surfaces that are, below the natural surface of the ground. Okay, they are sometimes referred with other names. So if you go to the if you go to the work site and you hear that people are referring or showing a hoe and they are using a backhoe or a shovel, don't get surprised. That's just another way they are called. So remember that hoe, backhoe, and shovel most of the time mean the same thing by the people who are on the job site. So um, they are particularly useful to excavate trenches which are again under the ground surface, the natural ground surface. They're very good for to excavate pits, for basements, and if they are in smaller sizes, they could be used for a variety of different earthwork operations. What do we know about them? Because of their positive bucket control, they are preferred to drag lines and clamshells. Well, if you remember drag line and clamshell, they are very limited in the direction they can move, while hose can cover a wide area, a wide radius of area, and they provide a pretty good, controllability for the operator because the operator can easily see where the bucket goes and adjust it for based on the needs. So, however, the bucket is most of the time not a big one. It's usually less than 1 cubic yard. uh, I mean, its volume usually doesn't reach to 1 cubic yard, while for some other machines we have a lot bigger buckets. But uh, the fact that it can move in different directions and you have pretty good control over the bucket makes it a very popular earthwork equipment in many construction projects. So let's get familiar with different parts of a hoe. What are there in a hoe? They're color coded. If you want to take a brief look, this picture only shows the main parts. So you should know what is a stick, what is a boom. This is the stick where the bucket is attached to. The bucket is attached to a stick, and the boom attaches or connects the machine with the stick. Okay, so this dark green would be the stick here. Sorry, would be the boom here, and this would be the stick. Okay, so the boom connects the machine with the stick. What moves the machine? So these parts that I just talked about are all solid parts. What makes the machine move are the cylinders. So the cylinder could be placed on the bucket, sorry, it could be placed on the stick, and they could be placed on the boom. Okay, so hydraulic cylinders that are on the boom, hydraulic cylinder that is on the stick, and obviously there is the last cylinder that can move the bucket in different directions. So you can get an idea that in a variety of different directions, the stick, the boom, and the bucket can move. So what else are there? Are the important parts? Are the major parts of a hoe? The engine, of course, which is behind the cabin, and there are different parts of the wheels or the crawler, which we don't really need to get into that detail in this course, but it's good to know some major parts of that. Okay, so buckets, there is a variety of different buckets for hose, and most of the time the main important the the important thing or the main thing that is different between them is the width of the bucket that changes its capacity and production of the hoe. So penetration force into the material being excavated is achieved by the stick and the bucket cylinder. And actually, like I said, they are the parts that make the machine move. Other parts are just solid steel. So maximum crowd force is developed when the stick cylinder operates perpendicular to perpendicular to the stick. Okay, so let's see what they are. Stick cylinder is this one. So when this is perpendicular to the stick, you can apply maximum pressure, you can exert maximum pressure on the ground. Okay, so as you can see in this picture, the production of a hoe highly depends on how we can fill its bucket. Are we fully filling it? Are we partially filling it, which is most of the time the case? Okay, so most of the time we cannot fill 100% of the bucket. That could depend on the distance between the bucket and the cabin, or the height of the height and the vertical distance. It means the distance between the ground and the bucket, as you can see in the picture. So depending on those two factors, different capacity of the bucket could be utilized. Based on that, we have this table that shows what percentage of the bucket could be used. You might ask why it can go above 100%. That's because you can have it in heaped, in heaped capacity where the, the bucket is totally full and there is extra dirt or soil on top of that, so it is heaped. That's why the fill factor could even exceed 100%. It could go up to 110%. And it mainly depends on the type of materials the machine is moving, okay, the machine is excavating. So if it is moist loam, it's sandy clay, which is really easy to excavate and move. You can fill the bucket, but let's say you're working with a hard clay. So in that case, you probably won't be able, let me fix this. You probably won't be able to, use the full capacity of the bucket. Okay, sorry about the technical problems here. All right, so that is the fill factor, and that is a determining factor in finding the production of a hoe. So let's see a hydraulic hoe with land clearing grapple. So if you want to select a hoe, there are different factors you would take into consideration. One is the maximum excavation depth of a hole. Second one is maximum working radius. So do you need a lot? Do you need to cover a large area or a smaller area? So the radius of the area would impact, the choice of the hole. And maximum dumping height, it means to what height your bucket should go up and it can dump, and then it can dump the load. That could, impact the choice of the hoe. And of course, the hoisting capability, it means the handling pipes and the trench boxes, okay, all of these factors could have, could show you which hoe you would select. So obviously, just look at the video at this point. So if if you need to dump your load in a higher, elevation, or if the truck is in a higher elevation, your bucket should be able to go high enough to dump its load. And obviously, sometimes your machine has to rest on a surface and then send the bucket, on the edge of a surface, and then the bucket goes into something like a valley or something like a trench or a pit. So you would need a longer stake, so your machine could be situated safely in one location while its stake can, reach areas that are a little far from the machine. Okay, so depending on all these factors, you would choose a hoe that does the job smoothly for you. Sometimes hose, instead of a bucket, you could install a hydraulic ram into them. And what they do, the hydraulic ram, what it does is that it, especially when you're working with hard materials like rocks, it could shatter the materials into smaller pieces, which facilitates excavating them. Okay, and they are super powerful. Once again, the maximum power that they can apply on the earth happens when the stick cylinder are perpendicular to the stick. Okay. All right. So special round bottom hole bucket are this. As you can see, the teeth are welded, or sometimes they are removable because they're actually a very important part of the bucket. They start the cutting, okay, and they go. They depreciate very fast. So many of these teeth are replaceable. All right. So let's say we want to know the productivity of a hoe. What should we do? So technically, hoes and shovels have the same mechanism to find their productivity. We use the same strategy, and hoe cycle times are approximately longer compared with shovels. Okay, it means shovels are comparatively quicker machines compared with hoes, because hoes are 20% less quick. So optimum depth of a cut for a hoe depends on some factors. Obviously, the type of material is the first factor, the size of the bucket is another, and also the type of the bucket could could impact the optimum depth of cut. So the optimum depth of cut, as a rule of thumb for a hoe, is between 40 to 60% of the machine's maximum digging depth. Okay, so whatever is the maximum digging depth of the machine, 40 to 60% of that would be the optimum depth of the cut. Okay, so there is a table that shows the cycle times of a hoe, which we will see in next slides. So the elements of the cycle time for a hoe are, yes, this is the table. So yeah, these elements are pretty much the same. I mean, they do not vary a lot, but they mostly depend on the size of the bucket. Okay, so for example, for a bucket that is less than 1 cubic yard, you would see it takes, for example, 5 seconds to load, 4 seconds to swing, 2 seconds to dump the load, and then swinging back to position would take 3 seconds, and so that makes a total cycle time 14 seconds. While if the bucket is bigger, the biggest we have here is 5 cubic yard. That's a pretty big bucket for a hoe. So as you can see, the times are now bigger. Loading would take 7, swinging 7, and the rest of the durations are given. So it makes the total cycle time for a 5 cubic yard bucket 24 seconds. It takes almost half a minute for one cycle of excavating, swinging, dumping, swinging back, and then starting the next cycle. All right, so the basic production formula is this. As you can see, so 3600 seconds is just to convert, it's just to convert seconds to hour. So in 1 hour, there is 3600 seconds. But what is Q? Q is the hipped bucket capacity, okay? And we consider a 45 angle on top of the filled bucket, okay? The extra load is considered as 45 degrees on both sides. So my camera today falls, I don't know why, for any reason. I have to fix it. So what is the next item? The next item there is F. F is the bucket fill factor, okay? It means what percentage of the bucket are you filling? We just talked about it. It could vary up to, the maximum number we had was 110%, and sometimes you could fill only half of the bucket, okay? So T is the cycle time in seconds. So you should consider all loading, swinging, dumping, swinging, empty. You sum up all those seconds and you put it as T, which is the time it takes for one full cycle. What is E? E is the efficiency. For example, how many minutes per hour the machine is working efficiently. If it is 50, you would put 50 over 60 because there's 60 minutes in an hour. And at the end, there is volume correction. So you should always look at the problem that what kind of volume it is asking for. Is it asking for bank, loose? And accordingly, you can sometimes, not always, sometimes you have to adjust or convert your volume into what the problem is asking. Yeah, for loose volume to bank volume, from loose to bank, you would multiply the loose by this number, and from loose to tons, if you want to convert it to tons, you just divide the number you have by 2,000 because there is 2,000 pounds in 1 ton. So let's do a problem and see how we solve such problems. Okay, a crawler hoe having a 3.5 cubic yard bucket. So this is the size of the bucket. We need this to use the table because the many things in the table will depend on the bucket size. So We don't really use it directly, but we will extract a lot of information from this. So what is the bucket fill factor? The bucket fill factor, it depends on the type of material, so you should take a look at what type of material. Excavate very hard clay. Okay, so hard or tough clay is the last one, and it ranges between 80 to 90%. We can use, since it's not saying to go for the pessimistic or optimistic, we just take the average of between 80 to 90%, that would be 85%. So we just take that as the fill factor. Then optimum depth of the cut is between 30 to 60% of the maximum digging depth. Okay, so we have a table. From this table, what we can get is that, okay, it depends on the size of the bucket. Remember, I said we needed to use the information, the tables. This is one example. The size of the bucket here is 3.5. And what else do we know? It says having a loading height of 9 feet 9 inch. Okay, so because of that, we can get that the maximum digging depth ranges between 23 to 27%. Now, we should just check if actually, so what is number 8? Number 8 is soil boring information indicates that below 8 feet, the material changes to an unacceptable slit material. So we should just make sure that it won't go below 30%. Okay, so I mean, it won't go below. Yeah, it won't go below 30%. So the range was between 23 to 27. So we do the calculations for the two sides of the range. One of them would be 8 over 23, which is 34%, so it is okay. The other one is 8 over 27. Again, it is 30%. So as long as it is not less than 30%, that is acceptable. So we make this check and we are good to go. It means we can do the digging at that height. Therefore, under average conditions for a 3.5 cubic yard size hoe, cycle times, so how can we find the cycle times? There is a table for that, okay? That also depends on the size of the bucket. Size of the bucket here is 3.5. So what kind of, so the seconds, the durations in seconds for different elements of a cycle are given in this table, and we actually just care about this 22. So we know it takes 7 seconds. It takes 6 seconds. It's 7 seconds to load the bucket, 6 to swing, 4 to dump, and 5 to return. That gives us a total cycle time of 22 seconds. Okay, so now all of the elements of that formula, that equation are available. So we can just, and the efficiency is 50 minutes an hour. So we can just insert it. Okay, so since we need to convert it to, let's see, what is the estimated production rate in cubic yard? Okay, bank measure. So we need to convert loose to bank. That's why we need to know the swell factor. That could be found from table 4.4. The swell factor for hard clay, we can see it is 35%. So, and yeah, the material is, it says hard clay, very hard clay. So we can consider it as dry clay, which is harder than wet clay. Okay, so Having that percentage, now the production, we have, all the elements we would need to find the production. So we just insert the numbers we had. 3600 was the constant. So 3.5 was the volume of the bucket, but only 85% of that would be filled. That was the average between 80 and 90%, if you remember. And the cycle time is 22 seconds. Cycle time is 22 seconds. And the efficiency is 50/60, right? So not the entire time is being useful, but 50 out of 60 is the useful time, is the efficient time. Then we have to make this conversion to change loose to bank cubic yard. If you do the math, the answer would be 300 bank cubic yard per an hour. Okay, so this hoe can excavate 300 bank cubic yard in 1 hour because of its bucket size and because of the material it is working with, and of course the height of the digging depth. We should make sure the digging depth is okay, and because of the efficiency, that 10 minutes of an hour it's not working efficiently, but it will work 50 minutes an hour efficiently. So this completes our lecture about hose. I see you guys next time.